Tá. Testando. Ok. Poxa, me escuto com uma voz bem distinta, viu? que não tem jeito, né? Fala mais um pouquinho. Mais um pouquinho. Do you hear me? Vocês conseguem me escutar?
Yes, yes.
Ok.
Hello, could you check my phone if it's, do you hear me?
Yes. No. Liga aí. Yes. We can hear you. Is everything all right?
Maybe my microphone is not so good. I don't know.
We can listen to you. I don't know if we have a
Oh, no,
problem
it's
in
perfect.
here.
I hear you. Yes.
Now it's okay?
Okay.
Okay.
Thank you. Do you hear me? It's my voice.
Yes.
Okay, excellent. Thank you.
Thank you. We are going to wait 5 minutes and then we will start.
Sure.
Okay. Tá ligado. Tá ligado. Daí, quando for a hora das perguntas, eu levo esse microfone para as pessoas da plateia. Mas acho que a gente também está aprendendo. Você me fala a hora que você quiser começar?
Então, vamos esperar às 14 horas.
Você podia filmar ele apresentando, né? Você consegue fazer isso?
Como tem gente online, é melhor esperar às 14 horas. As pessoas chegam. Então, um perigo, né?
Sim.
Professor, aquele ali vai ser usado também?
Ele ali está filmando a plateia.
O slide, sei lá.
Não, ele vai fazer tudo.
Só o quadro.
Quem é o Sherman?
Então a gente troca no quadro.
Você? Vamos esperar às 14 horas.
Sim, que boa.
O pessoal está online.
Não, acho que é ótimo, tá na hora.
E esse aqui, deixa eu fazer aqui.
Vai deixar pra
Hi, Alex.
Hello, Zbigniew.
How are you?
I'm fine. Are you struggle with the correction of the paper?
Yes. I work on this exactly now.
Ah.
I think it all will be okay. I have this new modified version, and I simplified these proofs, mine proof.
Simplified? What proof?
This mine proof of this local version, because local version can be reduced to the global version, and I would like to do this. Yes.
I see.
And in fact, we have almost self-contained paper with one exception. This degree, the degree of the link is the same as the degree of the multiplicity. Yes. Because we use, but probably it's okay, yes, because it's not possible to prove everything in the paper. Yeah,
Yeah, of course.
And you know that Lev is in Poland. Yes, he was in Warsaw.
That's easy.
Yes.
He sent me some pictures.
Okay. Probably something starts. But now Sampaio has a. Okay, bye.
Bye.
So, good afternoon, everyone. The first speaker this afternoon is José Edson Sampaio from Universidade Federal do Ceará. And he's going to talk about the global Bi-Lipschitz classification of semialgebraic surfaces.
Okay, thank you. Thank you for the invitation to give this talk in this nice event. I'm going to talk on classification of surface that can have maybe singularities and maybe are not compact, for example. Let me, for instance, say what means Bi-Lipschitz here. I would consider Bi-Lipschitz with respect to the inner distance. Okay, so if you have a path connected set in Rn, for example, we denote by dx in 2 points of x by the infimum of the length of curves of arcs connecting gamma connecting x and y. X and y, for example. So I will say that a map phi from x to y is in a Bi-Lipschitz. In some moments, maybe I will say only Bi-Lipschitz, but if I don't say anything, I'm considering Bi-Lipschitz with respect to the inner distance. Okay, so is inner Bi-Lipschitz if there exists some constant c greater than 0 such that 1 over c dx x and y is less than the y phi of x phi of y less than c dx of x and y. Like the talk of Zbigniew in this morning, for example. Okay. In fact, Zbigniew considered the outer distance. Here I'm considering the inner distance. Okay. I will say that a set is L and E, Lipschitz normal embedded. X is LNE. Let me only say LNE here, but means Lipschitz normal embedded. If there exists some constant C greater than 1, such that the inner distance is less than C times X minus Y for nx and Y and X, okay? So this is an important part of our work to understand which kind of sets are LNE. In fact, if you have two sets that which are LNE, and we have an inner Bi-Lipschitz homeomorphism between them, because they are LNE, this inner Bi-Lipschitz homeomorphism need to be outer Bi-Lipschitz homeomorphism, for example. Okay. So let me remind, for example, the well-known classification of smooth compact surface, for example, theorem of classifications. We know, for example, if let X and Y be compact, smooth, connected surfaces. So the following things are equivalent. 1, X and Y are homeomorphic. 2, X and Y are diffeomorphic. Third, the orientation that let me represent the orientation of a set. For example, I will say this number of X is 1 if X is orientable, and minus 1 if is non-orientable, for example, okay? So if they have the same orientation, for example, they have the same genus and genus, okay? Orientation and genus. And the genus of X is equal to the genus of Y. And now, because the inner Bi-Lipschitz homeomorphism between compact smooth manifolds lives between the homeomorphism and diffeomorphism, of course, we can add a fourth one, X and Y are inner, let me, I will say also lipiomorphism instead of Bi-Lipschitz homeomorphism. I only say lipiomorphism, okay? Inner lipiomorphic. I think it's time to use this word to represent Bi-Lipschitz homeomorphism, okay? So we have this one. So let me do some remarks about this classification. If you remove, for example, one of these two words, compact or smooth, for example. If you remove compact, we can consider now, let me consider still closed sets, okay? Smooth closed sets in maybe some Rn. But now, maybe non-compact sets. For instance, example, we can see, for example, the genus of the cylinder. Let me call X the cylinder in R3, such that X squared, Y squared equals to 1, and Y is R2, for example. They are both are orientable. They have the same genus, okay? But they are not homeomorph, for example. And how it's easy to see that. No so easy to see example is, let me call example A, example B. We still consider y is equal to R2, but Z is now the graph, this guy, this the parabolic surface, x, y, z in R3, such that z is equal y square plus x square. Okay. Now this is a graph of a smooth polynomial. So of course this is diffeomorph to R2, but it's a good exercise to prove, for example, they are not in a Bi-Lipschitz homeomorph. It's a good exercise. It's a good homework for you to prove that. So as you can see, if you remove the hypothesis of compact, we need to put more invariants here in our combinatorial invariant to get in a Bi-Lipschitz homeomorphism, for example. Okay. Even if you assume smooth, for example, no? And if you remove smoothness, and now appear all the kind of problems. For example, let me draw another example. For example, we take the cycle, the sphere, like that, and we take the hard, like a surface like that, and here is like z cube equals to y square plus x square plus y square. Okay, something like that. If you have, of course, they are homeomorphic, right? But if you consider, if there exists some inner Bi-Lipschitz homeomorphisms, this point is sent in some point here, but we can prove also this kind of thing cannot happen. We cannot obtain an inner Bi-Lipschitz homeomorphism between something like that to something like that. For example, like some smooth thing to something like a horn, no? 3/2 horn, for example, like that, right? This, in fact, follows from an important theorem proved by Lev-Bibraï. In fact, our ideas follow the ideas in that paper. In fact, Bibraï proved the following theorem. I will call here this theorem of Bibraï. Okay, theorem of Bibraï. He proved the following. If given X a germ of a surface in some point A with the link, with connect link with isolated singularity, with isolated singularity, at, let me call P because P, okay, at P, and with connect link, and with connected link, connected link, at P also. So then there exists a unique beta greater than 1 and rational number beta greater than or equal to 1, such that this germ xp is lipomorphic, inner lipomorphic to x beta 0, where x beta is this guy, is x, y, z in R3, such that z equal power 2b is equal to y square plus x square plus y square, and z is greater than 0. So in other words, any surface with isolated singularity and with connect link is lipomorph to some beta horn, because this is just some horn like that, right? Locally, it's just something like that, some beta horn, and here I'm putting 2 beta like that. And this is a one horn. A smooth point is a one horn, and so this guy is lipomorph to one horn, but this guy is lipomorph to a beta horn, but because it's unique, they cannot be a lipomorph, for example. Okay. So I want to say what is my invariant. I want to define what is my invariant and try to give some hints how to prove. In fact, this is a complete invariant for surface with isolated singularities. So in order to do that, let me consider some surface, some semi-algebraic surface closed in Rn and with isolated singularities. Okay. Let me consider Rn like that. And since we have, for example, conical structure theorem at infinity and at each singularity, for example, we can find some R0 greater than 0, in fact, greater than 1, for example, such that x is equal to x minus the ball. Let me x minus the ball of r of radius r 0. In fact, for n r now greater than 0 r0, this guy we can decompose in the following way. Everything outside of the ball of radius r, and everything of radius inside of the balls. Let me write in this way: P in this set of singularities of x. Okay, singularities of x, and here I will just do like that: 1 over r p, and of course now I remove the ball of radius r. I included the ball of radius 1 over r with center p, and now we have also some compact part, which is, since we are taking r big enough, we can consider, for example, the intersection of x with the sphere. The boundary of this ball is intersecting in a transversal way. So this intersection is smooth, for example. Also here, you can consider R0 big enough such that the intersection of the sphere of radius R intersecting in a transversal way of x. So this guy is a compact manifold with boundary, for example. Okay. So here, for example, now we have this intersection has some, the link has some connect components. Let me say LP, the number of connect components of this intersection, for example. But now each connect component of these guys is a surface like that. Is a surface with isolated singularity and connect link. So there is some number, a beta, for each connect component like that. Let me just for a moment, if I fix on P, I fixed P, for example, P in the singularities. This guy, this intersection. Let me. I have to erase that. Sorry. This X intersection with the ball of radius 1 over RP is the union of xi, I equal to 1 to some, let me call LP, just to, LP is the number of connect components of the link. So now this guy, each xi is a surface with isolated singularity at P and has connect link. So there exists some beta I such that xip is, let me denote here for brevity. This is beta I 0, for example, right? The beta I horn. So we can, by reordering the indices, we can assume, for example, beta 1 is less than beta 2, such, beta LP, for example. And I will denote beta of x at P to be this vector, the beta 1 up to beta LP. This number is a part of our invariant. I will define more. Okay? So we have this invariant. This invariant, we have two information in this invariant. We have, at the same moment, the number of connect components is just the dimension of the vector. And of course, the Lipschitz type of each connect components is saved here in this. We have these two information, okay? Here, when we remove a ball with radius large enough, we have some connected components also, which we call ends of our surface, okay? And also, we can prove, I would try to give some hints how to prove that. We can prove, for example, let me erase here. We can prove x minus the ball of radius r is some union of ends, let me call by E to remind of ends, I equal to 1 to E of x, the number of ends. And we can prove each end of that is in a Bi-Lipschitz homeomorph at infinity by removing some compact set to some guy like a pipe. Let me put pipe beta I. And this guy is just x, z, like that, x, z greater than, in fact, I can put, I think it's a rotation, I think it's like that, right? Z 2 beta equal to x squared plus y square. After removing some compact, right? It's a p minus some compact k. You can, for example, remove, you can put x greater than some positive number a, for example, okay? In fact, if you think this guy is more or less the same of a horn, but here for a horn we have beta greater than 1, but here beta is less than 1. And beta is between 0 and 1 here, and for the local case is greater than or equal to 1. Okay, so you can prove that. If you can prove that, we also have, like here, some invariant called like we can have this beta I to the end ei. So we have the beta infinity, and this is beta beta 1 also up to beta e of x, the number of ends. Also, I ordinate this by doing just like that, right? Beta 1 is less than or equal to beta 2, etc. So, okay, our invariance is a little bit more complicated that I will present now. I will consider one specific case. Let me assume, for example, x. This is well defined if x has the regular part of x is connected or not. But I will assume the regular part of x is connected, okay? For example, let me assume the regular part of x. That means x minus the singular part of x is connected. If this is true, I will define the Lip code, say the Lipschitz code of x to be the following collection. We collect the genus of this compact part. In other words, this in fact is the genus of x. Let me denote the genus of x to be the genus of this compact part. I will define the orientation of x to be the orientation of this compact part also, like before. Right? So the orientation is 1 if k is orientable, and -1 if k is non-orientable, for example. So you have orientation of x. We have genus of x. We have a collection of let me put in this way. Let me this collection. Okay, beta of x p, when p is in the singular part. And also we have beta of x at infinity. Okay, we have this information. I separated these two guys because I want to know which information comes from the infinite part and which information comes from the finite part, for example. So the theorem is the following. So I can, if you have this is the Lip code. So the theorem is to surface like that. I'm assuming in fact, if is not connected, we can define the Lip code, but it's a little bit more complicated. So I will not define it. In fact, I don't have time. So, but the theorem is the following. The theorem is x and y are closed semialgebraic surfaces, okay, with isolated singularities. Then we have the following. Then X and Y are lipomorphic if and only if the lip code of X is equal to the lip code of Y. So, in other words, we can describe the Lipschitz geometry of a set just by some combinatorial invariant, by a numeric invariant. Okay, like we could done for compact smooth surface in the differomorph case, for example. Okay. So I have some minutes. I think I can say some hints about. In fact, the main part of the theorem is prove that, because if I prove that by the theorem of Bi-Barajas, we can, of course, obtain this part of the Lipschitz invariant, the finite part. And if you know this, also there is a part to prove, for example, this is a Lipschitz invariant, in a Lipschitz invariant. And also, of course, no, it's not so hard to prove this implication. Lipschitz, if they are lipomorph, then the lip codes are equal, for example. So the harder part is, for example, if you have two sets with the same lip code, then show they are lipomorph. So we have, for example, because that we can find the lipomorphism, because of course, if you have if these two numbers are equal, for example, no, like beta of y at infinity, so we have this. In fact, these two vectors are equal. So of course, if EI is in a lipomorph to this guy, and the EI tilde for y is also lipomorph to this guy, or we can obtain, for example, a lipomorphism between the corresponding ending EI to the corresponding end EI tilde of y, for example. So we can obtain inner lipomorphisms between the ends, inner lipomorphism between the finite parts of the intersection with the small balls with center in the singularities. So, and because we have now a compact K is a compact surface with boundary, and that surface has the same genus, the same orientation, and the same number of boundary components, because the boundary components comes from just the number of connect components of the link in the singular part, and also the number of ends. But we are assuming that the number of ends are equal, and the number of links also are equal. So we have that compact parts has the same three invariants: genus, orientation, and number of boundary components. So the classical classification of surface with boundary, they are diffeomorphic. So if they are diffeomorphic, they are lipomorphic. So we use some trick to glue these parts, and we obtain, we end the proof. So if you understand, you understood very well what I said just now, how to catch the information and then glue. The main part is to prove this. If you can prove an end, in fact, it's lipomorph a pipe, a tube like that, right? And the way to do that is a little bit technical, but the point is we first define what means a strip, something like that, some infinite triangle like T beta is just y in R2, for example, such that 0 less than y less than x beta, and x we fix some a greater than 0, and we assume x is greater than a, for example. In order to draw something, it's something like that, right? It's, here is a, so we have something is like a surface like that, right? This is something like that. So what we can do is we can take the pancake decomposition for semi-algebraic sets, proved by Kurdica and Paunescu. And if you have something like that, you can write this guy has a union of some semi-algebraic sets, and the semi-algebraic sets, we can prove each semi-algebraic set is outer Lipschitz homeomorph to something like that. Because we can prove they are inner, but by the pancake decomposition, let me write in order to, we can write some end, let me call just E by the end, some union of some xi's, and now what I'm saying is each xi is some LNE set, and we can, in fact, this the pancake decomposition gives a more or less exact description of this guy. In fact, this is a band or a graph of a function with a derivative, bounded derivative, for example. This is an inductive process, for example. So you can prove, in fact, by this condition of bounded derivatives, we can prove each guy of that is inner by Lipschitz to a guy like that. And because this guy is LNE, we can prove also this guy is LNE. So it's outer by Lipschitz to a guy like that. And then we can prove, for example, if you have two guys which are lipomorph to a guy like that, we can define, for example, an invariant, like we can say, for example, if a guy is an inner lipomorph to a guy, T beta, for example, we can say this is a beta strip. And we show, for example, this beta is well defined. That means if you have two betas, if you have an inner lipomorphism between T beta and T beta prime, for example, then beta prime is equal to beta. So we can prove that. And this also is a technical part because we have to define what means contact of two arcs at infinity. And here appears some problems because when you are in the local case, when you define contact, you can define the distance between the ball or outside of the ball, or just in the sphere of radius r and take the exponent of when it is expanding the Taylor expansion of this guy. And these three definitions give the same notion, the contact of two arcs at that point. But at infinity, we have a problem because when you take outside of a ball, this is generally is unbounded. The distance is not bounded, for example. So you cannot define in this way. So there is a part to define this notion in a nulli, for example, and then to show that the notion does not depend of the width of the annuli, for example. And with that, we can prove the beta is well defined. And then we prove after that with glue two a beta stripe. I don't know if it's stripe or strip. I don't know how to pronounce this. But if you glue two guys like that, this gives another guy, which is the same type of the maximum of the beta. So you have beta 1 and beta 2. The union is some t beta and beta, where beta is the maximum of beta 1 and beta 2. All right. Okay. So if you have, I'm almost finished the very poor idea. So if you have E and you know that E is a union of beta strips, and then if you know E is a union of beta strip, and you know if you have two strips with arc, the intersections are arc, so the union is just the maximum of the two betas. And then you do that after a finite time, a finite number of times, because this is finite, like some R. We return to the same initial arc, for example. So, in fact, we can, in fact, in the end of the process, we can prove after some R times, we can prove, in fact, the union is just in the Bi-Lipschitz, something like that. And then we are done. That's all. Thank you very much.
So thank you very much.
W podsumowaniu drugiego newsa, mianowicie chodzi o to, że artykuł 5 wskazuje, że jeśli jakieś kraje NATO zostaną zaatakowane zbrojnie, no to wtedy inne kraje NATO mają to potraktować tak jak atak na siebie samego i
I did not understand.
Any
Sorry, can you
question?
repeat?
So,
Hello, Edson. Thank you for the very nice talk.
Thank you.
Yes. I'm like to ask maybe some specific examples in order to understand this nice classification. For example, it seems that to take a graph of z equal to some homogeneous polynomial, like you given the start of your talk, then suppose you have a z equal to some polynomial from order d, and you take some deformation, but now you take a sum of polynomials of the degree less than the initial order, right?
Sorry, I will try to write what you are saying. Okay, let me. You took some x, which is a graph of some f. F is something, a homogeneous polynomial.
Z equal to some, for example, z equal to x squared plus y squared, for example.
Okay.
No, take x4, for example.
Okay. F is x4 plus y4. Is that this?
Yes.
Okay.
And then if you add the x3 plus y3, for example, and these are Bi-Lipschitz equivalent and infinite.
That is, are you saying that is Bi-Lipschitz equivalent to let me call f, and G is f plus. Is that your question?
Yes.
So
that you default
the graph of f and the graph of y. I think yes. I think they have the same Lipschitz type.
Because in the locally is not, but infinite it seems that you take
yeah,
a
but
small
the point now, if you take the graph locally, there's no problem because this is smooth.
Yeah,
you are taking the graph,
no
there's no problem for in the smooth
the
case.
The point isn't infinite.
So the genus is 0. The that's a graph is orientable. So the unique invariant that's important is the number of ends, which one is 1 because it's a graph. And now the unique important invariant is the beta for each one. And more or less the beta is a measure how faster the link disappear at infinity. The link at infinity, it's more or less the same. But I think both the link disappear in the same velocity, I think. So this is why I think maybe I could not hear. Because the order in this case, we don't care about the order. The unique important information at infinity is the degree. Because at infinity, these disappear after. That's the point. At infinity, we don't care about that. And locally, this is smooth. We don't care also. So that's the point. So they are in a Bi-Lipschitz. So no.
So,
but for example, this gives away. For example, so just to say some word. This guy, that example that I wrote in the beginning, the half of the talk, the parabolic surface is not homomorph, Bi-Lipschitz homomorph to the plane, for example, because the plane, the beta is equal to the beta. Here is a beta greater than x, z is greater than 0. Okay, sorry. So it's beta equal to 1, for example, and that one, the parabolic is beta equal to 1/2. So they are different. They have different lip code. Another way to, but we can prove directly. But a way to see that is maybe the way to prove directly is reading our paper. Maybe the ideas is more or less like the same.
Okay, any more questions from the people that are online? Any questions? So let's thank the speaker again.
Thank you.
5 minutes for the next. Okay, 4 minutes, 5 minutes for the next speech, okay? pergunta para ele.
Agora ele vai apresentar, mas ele vai apresentar com o slide. O seu, né?
Vai.
Você é Marcelo Saia?
Sim, teoricamente sim. Não acharam outro. Não tem nenhum homônimo. Por quê? Tem alguma coisa contra? Deixar isso aqui nas minhas costas.
Aqui você está no ICMC.
Isso aí não fui eu que coloquei, não. Isso aí não fui eu que
Você está
coloquei.
na federal agora.
Alguém sabe colocar em tela cheia?
Não precisa. É, eu não sei de onde veio esse ICMC, porque isso aqui está do meu artigo, já não é mais ICMC.
Vou colocar aqui da
UFSCar. O meu...
Lá está escrito
Lá
certo.
está escrito certo. Isso aqui eu não sei o que aconteceu.
Que é do
Veio com o meu endereço antigo.
Ah, nossa.
E eu mandei...
Esse aqui também não foi eu que fiz.
Ah, é o hábito, com certeza. Não se
Eu vou
preocupe.
mudar.
Não se preocupe, mas tem que mudar depois, tá? Isso aqui eu faço como?
Essa. Esse. Isso.
Eu estou escutando aonde, falando aonde.
Isso. Aqui tá no mudo. Clicou uma vez e vai ficar verde. Aí tá funcionando.
Testando. Vocês estão escutando direitinho? Beleza.
Vou colocar no mudo e só
Você vai colocando no mudo e eu vou esquecer de mudar.
se esqueceu o disso. Eu vou trocar logo.
Sem pressa.
Esse monte de gente aí vai resolver rápido.
Deus queira. Eu acho que não. Chama o Paulinho. Se tem um monte de gente assim, é porque ninguém sabe o que fazer.
Ninguém sabe botar em tela cheia.
Imagina, gente.
Você acertou.
Todo mundo doutorado. Doutor.
Me dá o computador aqui que eu arrumo, gente. Se eu for pôr em tela cheia, deixa eu arrumar esse PDF, vocês estão perdidos aí. Põe ele para mim aqui. Aonde eu vou falar?
Cadê o microfone?
Eu tô. Acho que sim. Só que não tá ligado ainda.
Então tá tudo certo. Ó, aqui você
Posso
passa-
começar?
Peraí, ele vai te apresentar primeiro.
Não, eu sei.
Mas agora você pode passar aqui.
Colocar em tela cheia.
É, tá desse jeito. Eu não consegui tirar aquele negócio de cima.
Você não vai conseguir.
Tá.
Ninguém consegue tirar aqui. É da barra de ferramenta.
Tá.
Maravilha.
Consegue passar? E acho que tem algum lugar que tem a luzinha. Acho que é aqui no meio. Tem a luzinha. Tá.
Maravilha. Legal. Oi, você está me escutando? Essa mochila aqui? É que senão eu vou esquecer ela aqui. Não, é medo de deixar. Maravilha.
Sei lá quanto ele vai durar agora. Esse aqui fica com a pergunta. Você que vai apresentar.
Onde que está a mudança de páginas? Só um segundo. Onde está a mudança de páginas na barra de ferramenta? Deveria ter mudança de páginas da barra de ferramentas, mas deixa, não tem problema. É que eu vou precisar pular de uma página para outra sem ser na ordem. Não precisa pôr na tela cheia. Mas eu passar da 13 para 47 e voltar para trás. Aonde? Aí? Ótimo. Pode deixar. Então aqui eu resolvo. É só colocar e digitar. Maravilha. É porque eu precisei trocar de página, tá? Vamos começar? Por favor, um prazer.
So let's start. I have a great pleasure to introduce my friend,
Great friend.
Marcelo Saia. Now he is from UFSCar,
UFSCar.
from São Carlos. And I am very grateful you are here.
Thank you.
And he's going to talk about Bi-Lipschitz and the i-sufficiency of weighted jets.
Okay, thank you very much, Vladimir. It's a great pleasure for me to be here after a long time in my house. And Vitória is a very special city for me. I like too much to be here. So I am very happy. Thank you very much, the organizers, for this invitation. And I want to congratulate you, the organizers, to realize this workshop, because the situation is improving now, and they are really doing a very nice work, a very interesting work in doing this mix between presential and online talks. I want to congratulate them. Now I'm going to talk about Bi-Lipschitz and C sufficiency of weighted jets. This is a joint work with João Carlos Ferreira Costa. João is from São José do Rio Preto, IBILS, Unesp. And Carlos Humberto is from University Federal of Piauí, from Teresina. And this is a joint work that we are doing for some time. The results of this paper will appear soon in Journal of Singularities. And now, let's go. The beginning of this work is the beginning of the singularity theory, in fact. It is a history. The sufficiency of jets was introduced by René Thom to establish the structural stability theory. The structural stability theory of singularity theory is the first theory developed. Is the main theory developed for this. This is a very famous paper of Thom, 1964. We are in 2022, not a long time ago, okay? Just to introduce some notation before going to the history. It's important to emphasize the history of this work. And we are considering map germs from Rn to Rp of class Ck. K is some integer from 0 and infinite fixed. And map germs, okay, P is bigger or equal to 1. And we are looking to the R-jet of these germs, the space of jets of degree R in this set of map germs, okay? This is the main subject of our work, but in fact it's a little bit more general than this. I will show you later. And we are looking just for the beginners that the R-jet is nothing more what is a jet? Nothing more than the polynomial, Taylor polynomial of the germ, of the map germ upstairs, truncated in the K degree, okay? This is called the CK realization of a jet in the jet space J, R, and P. Of course, we are looking for R smaller or equal than K. Because we are taking the derivatives, we cannot go up because of the class of differentiability of the germ. Equivalences. These are the main equivalences that appear in singularity theory, and we are talking about them. Okay? A pair of germs is SV equivalent if you have that homeomorphism from Rn to Rn such that the inverse image are left from the inverse image of one is left to the other through H. Just the inverse image of 0. On the other side, we have the V equivalence. If they are homeomorphic, like germs at 0, okay? But we have more. We have the topological equivalence. If this is a germ of homeomorphism, here is the ambient homeomorphism. Here is the homeomorphism just between the 0 set, and here is the homeomorphism as set, and here is the ambient homeomorphism. And here we have the Bi-Lipschitz equivalence. It's nothing more than the same condition, but we have ambient homeomorphism here, okay? Bi-Lipschitz, sorry. It's a little bit more than only a homeomorphism. Oh, it's not everything appearing there. There are something written before. I cannot see. Here, it is not appearing everything here. I'm sorry. Oh, thank you very much. That's better. Thank you. Here are the implications, okay? C0 equivalence implies the V equivalence, which implies this SV equivalence. The converse is not true, okay? This is proved by King. And the CA plus 1 implies the CI equivalence, and C1 equivalence implies Bi-Lipschitz, which implies the C0 equivalence. So we have a kind of star of equivalence, one implying the others, okay? There are some mixing in these equivalences between so I go back one of these. If you look to the C0 and the Bi equivalence of functions, there is some kind of common intersection, but they are not the same. Okay, there are some special conditions to have it like the same. And now we are talking about the sufficiency. Okay, the germs are SV sufficient, S0 sufficient, Bi-Lipschitz sufficient, and everything. If any two realizations, the realizations are the germs which have map germs from C to CK, which have the same R jet here, if they are equivalent. So we have the sufficiency. This is the definition of sufficiency given by Wall, but not for this. He gave the definition of sufficiency for the same finite sufficiency. And then these things become more developed later, okay? Beginning of this work, as I told you before, I am going to talk a lot of story on this talk. TCQO, C0 sufficiency of jets of potential functions. It's important to emphasize the functions here. Of course, we do things first for functions and later for map germs, okay? 1969, 5 years later, after the Reneton gave the question, he gave the same the first condition. C0 sufficiency is controlled by some inequality like this: a gradient bigger or equal than C normal of X R less 1. It's important to emphasize that we are looking R jets in JR and 1, okay? Here R less 1. When you do the derivative, the degree of the germ here goes down 1. This is why we are 1 jet less on this condition, okay? This is the most important condition given in all these papers, okay? What is the difference? How to control, better control, given a jam, how to better control this, but not just by the usual norm, okay? This is very good to control homogeneous jams, not to control weighted homogeneous or any kind of other jams, okay? Just to not forget, this is called the Keeper-Cool condition, okay? Because in 1972, 3 years later, it was published by Cooper, the same result then Cool. This is the Keeper-Cool condition. Good. The main question in this situation to control the zero sufficiency is to control this guy, to give a better inequality to control this guy. Oh, this is the converse of Keeper-Cool theorem, given by Bochner and Lojaszewski. This means that you have someone of class K plus 1, and if you have the sufficiency here, you cannot have the sufficiency if you go down to the class of differentiability, okay? Now I'm going to talk about the other condition. The same paper that, as far as I know, in the same paper that I told before, Reneton gave another condition, okay? And this condition was shown to be equivalent to Keeper-Cool condition, like I showed before, given by Becker and Koik a little bit later, 1998, okay? But before this, the tone condition, I don't know if people was literally working in the tone condition or in the other conditions, but I know that the results were given the other conditions. Sufficiency, as I told you, so important like this other sufficiency. The Sequo characterized it. Now we have, look, gradient of Zx bigger or equal than Cxr minus delta, okay? And this is quite a very usual condition. You need to control f of x by looking to the R jet of the jam. This is the condition given by this, okay? But it's important to compare here with this. The Keeper-Cool condition that I gave before for the C0 equivalence is R minus 1. This is R minus delta, a little bit difference. But if you are looking to jams of functions, we have an equivalence between V sufficient and C0 sufficiency, okay? But for functions, not for map jams. CI sufficiency. The CI sufficiency was studied by Takens for functions, okay? Not on sufficiency of jets, inventions of mathematics, but this is the main motivation of all these works. I needed to talk this, okay? But it's for functions. For p equal to 2, there is the paper of Favre and Martins, and we need to give a special mention for this paper. Sorry, it's not this. I will show you the proper reference. Favre was a teacher in São Carlos a long time ago, and Julio Martins at this time was his student of master student. I go to the proper reference here. This L.A. Favre, JCC Martins, Estudos e Pesquisa, em Matemática, 1981. The most interesting is that mathematics was done in Portuguese at that time. This is a paper written in Portuguese, published in Portuguese by a Brazilian revista that was published by Unesp São José do Rio Preto, not just by Unesp São José do Rio Preto, but a journal published by there. I don't know if it's already published nowadays, but was in Portuguese. The first result for map germs, sufficiency of map germs, one of the most important questions given by Reneton, was published in Portuguese. It's quite interesting to emphasize this. And then when we realized this, we said, okay, let's do something else. Okay, so for P bigger than 2, bigger or equal than 2, for map germs, literally map germs, the i-sufficiency was done by Faber and Martins, a fantastic work, very interesting. Oh, I go back, where is my notes here? Okay. Then we have one of the motivations of our work is the work of Paunescu, because he was considering the weighted point of view for the sufficiency. And this was the most important for us at the moment. Okay, this is a paper of Paunescu, very recent, comparing with the others. But it's a version for the V sufficiency, only V sufficiency. But in the weighted jets, J, R, W, and P. Here we are changing, as I told before, the jet space. Not changing the jets, we are changing the way that we look for them, okay? Here now, our results. A criterion for C0, CI sufficiency for weighted jets in JRNP, JRW, and P, with P bigger or equal than 1, okay? With these results, we improve the degree of C sufficiency given by tax for P equal to 1, and by Faber-Martins for P bigger or equal to 2. Our results are, in some sense, not in some sense, but literally more a generalization of these results, because if you consider the set of weights 1, 1, 1, 1, 1, 1, which is the usual degree that we look for the polynomials, we have the result given by Faber-Martins, as I'm going to show you a little bit later, okay? This is really a generalization of these two works. Moreover, we treat here the Bi-Lipschitz sufficiency. All that works that I told before, they didn't consider the Bi-Lipschitz sufficiency because they didn't know nothing about the Bi-Lipschitz geometry. Bi-Lipschitz geometry was developed in the 80s, after this theory, so they could not look at these conditions. Okay. It's funny because this condition was our first proposal. When we saw this paper, we saw, oh, this is not just a C0, C1, C2, C3 sufficiency, but there is the Bi-Lipschitz in the middle of this, between these conditions that we need to talk, okay? It's impressive that now there is someone calling me in my cell phone. Can you believe that? I am all time with the cell phone, but it's been calling now. But don't worry. Bi-Lipschitz geometry is much more recent than the papers that I was talking for you before, okay? Now I'm going to talk a little bit about the work given by Faber-Martins, okay, in the jet space JRNP, just to compare what we have done from what they did. This is a very technical condition. V1, Vp are the sets that we are going to consider later, is the gradient, okay, the derivatives of each one of the F1, F2 coordinate functions given by our germ F, okay. We need to do some kind of normalization of these vectors. These are given by this distance, they are, oh, sorry, it's not distance, but it's the, here is the distance. The IF, Vix minus Yj, Vj. This is what I told you, a kind of normalization. We are considering normal projection of one vector to the set generated by the others, and considering that distance. This vector that gives the distance is going to be the vector that I'm going to use and the control the vector field that I'm going to construct later. I hope to do it in time. And that Favaro-Martins calculated all the minimums and did called DV1, Pitakans, in fact, did it, the minimum of these guys, okay? And gave two conditions, R of Z. This is a condition given by the gradient. The distance between the gradient vectors is bigger than XL minus 1. You can see here L minus 1. This L minus 1 came from the derivative of the germ Z. If you do the derivative once, you have 1 degree less. So you need to compare these guys and also to compare these guys. Oh, but there is a big difference. Here is bigger or equal. Oh, here is smaller. Yes. Because I'm going to take the inverse of these vectors, I'm going to divide by these vectors, then I'm going to have an inequality like this to do the comparisons that I need later. This is the Favaro-Martins result. It's quite a technical result. Not easy to calculate, but with some 2 or 3 examples, you do it easily. If you have R minus RZ plus 1, minus I is the degree of i-sufficiency, okay? R minus R0 plus 1 is bigger than 0, okay? Then Z is i-sufficient, sorry, zeta, but I call Z. This is the result given by Favaro-Martins. He is already the result of Takens when P is equal to 1. Moreover, this first condition here is always bigger than 0. And these conditions is really the C0, the condition needed for the C0 sufficiency. So this is the result given by Favaro that gives this core result for the C0 sufficiency also, okay? Now I'm going to talk about the weighted jet space. Talk about the weighted jet space, I need to talk about the weighted homogeneous germs. Weighted homogeneous, we give a set of weights for each variable. Sorry if you don't see it before, I can show you some examples later. But if you do a set of weights for the variables, you need to have the same degree giving outside lambda k1, lambda k2, lambda kp. So we say that this k1, kp are the degrees of the weighted homogeneous germ, okay? They don't need to be equal, and even here, okay? These are the weighted degrees. Now we decompose any germ in the weighted parts of it, like we do it in the Taylor series, oh, the degree 1, degree 2, degree 4. We do the same, but for weighted degree 1, weighted degree 2, maybe we have some degrees which are not integer, but we don't care about this by now, okay? We are looking for germs of functions, okay? I'm going to show some examples about this later. So this number, K1, is the filtration of the germ, and this is the weighted jet space with weighted degree R, and with fixed set of weights W, W1, W2, Wn, okay? Nothing more a polynomial such that all monomials of the coordinate functions have the weighted degree smaller or equal to R, this, okay? If you look to the JRF, you are looking to the polynomial of degree R. Here is the same thing, but you are looking for the weighted degree R, okay? And we have also UFSCar realizations of the germs if they have the same R-jet, weighted R-jet. Here, it's a comparison. X6 minus Y3, X6 minus Y3 plus Y4, okay? If we look to this germ, we need to look to the result given by Favaro-Martins and the jet space, the 6 jet space in 2 variables, your function, okay? The 6 jet space is x6 minus y3. This is the 6 jet space, okay? But here we have someone that's in the 4 degree. So this guy does not have the same jet space in degree 6 than this. So we cannot apply the theorem of Favaro-Martins. This was the main motivation for us. Okay, I know that this guy is topologically equivalent to this. So if topologically equivalent, why we cannot reduce this for the sufficiency of jets considering the weight degree? When I say that they are topologically equivalent, I am applying some kind of classical result from some time ago that this is weighted homogeneous, this is weighted homogeneous, degree 6. This is of degree 8 because it's 4 times 2, the degree of this guy. This is bigger than the degree 6, so I know that these two guys are weighted topologically equivalent, so they are 0 equivalent, but they are not in the same 6 jet, okay? On the other side, as I told you before, if you look to the set of weights 1, 2, this guy is in the 6 jet, and this is in the 8 jet, the degree 8. So the 6 jet of this guy and the 6 jet of this guy, considering the weight 1, 2, is the same. So we can do something else, looking for this set of jets. This point of view, it's not different. The jets are the same, the Taylor series are the same, but you are looking at a different point of view. So just something. The results that you are going to use here were not known at that time also. They didn't know the weighted homogeneous condition. These things were, it's well known for a long time, but not for the topological equivalence for these things. This is more recent. Okay. Then we have the sufficiency given for the weighted jet space as the same, okay? The difference is that we are looking for jet spaces in this guy, okay? And then the main difference is here. We are looking for a set of weights, W, W1, W2, Wn. In fact, we are changing the metric that we are considering, okay? If we go back to that the condition given by the gradient condition here, this is bigger than C norma of x, modulo of xl minus 1. We are not considering the modulo as usual here, but we are considering the control function that's given on the other side, and I gave you in the other, oops, here, okay? If you put S1, S2, Sn, and Q, all then equal to 1, we have the usual distance here. So we are changing the distance to do these computations, okay? This is the weight distance. A ball here is ellipsis, not more a ball, okay? But it's the same situation with different control, okay? This is the difference. We are looking to this control to do the computations. Now, we are changing everything using the control function. You can see that the condition D, gradient Z1, gradient Zp, bigger than rho x L minus 1, is not more here 1, it's Wn. Wn is the bigger of the weights. We are considering a set of weights that are ordered. You can do it all the time, okay? And why appear the L minus Wn here, Wn? Because we are doing the derivatives. When you do the derivative in the weighted homogeneous case, the degree goes down the weight of the variable that you are doing the derivative. This is quite usual to do, okay? But this is a control for the gradients. This is the guide that we are going to use to construct the vector fields that gives us the integration for the germs of diffeomorphisms, Bi-Lipschitz, or these things in the future. And this condition is just the condition z of x is smaller or equal to c rho xl. This is the condition that came from this, okay? If it is in this jet space, the zero jet of this guy, the r jet of this guy is 0, and then we have this condition. This is the main situation that we need for our theorem. First, the Bi-Lipschitz sufficiency. RW of Z is smaller or equal than R, and R bigger than 1. We need R bigger than 1 here. So we have that Z is at least a Bi-Lipschitz sufficient in CR. The condition here is the same given by Favre-Martins, okay? But they said, oh, this is C0 sufficient. But when we see the proof, in fact, we see that it's Bi-Lipschitz sufficient. This is nothing more than the result given by Favre-Martins, just looking for the point of view on the Bi-Lipschitz sufficiency, because the condition that they give is a Bi-Lipschitz condition, okay? Example, x6 minus y3. This is my favorite example. This is weighted homogeneous, degree 6. For the degrees 1 and 2, 6 times 1 is 6, 3 times 2. Oh, this is changed here, sorry. It's 1, 2, not 2, 1. Even in the paper, it's published wrong. This should be y6 minus x3 to have this weight, okay? Oh, sorry. This is n and p. This is the weight, 1, 2, sorry. He's already 1, 2, weight 1, 2, degree 6 here, okay? This germ has weight degree 6. Now we look to the same example that we gave before, that we cannot apply the result of Favre-Martins. But now, as I told you before, this has weight degree 6, this has weight degree 8. So these two guys, I believe, it's equivalent. So, okay? This was not possible to conclude using the result of Favre-Martins. This was the main motivation for us. Okay, to prove, the proof is quite technical. We need to construct a controlled vector field. From the controlled vector field, we do the integration of this vector field to get the homeomorphism, the Bi-Lipschitz homeomorphism, the CI homeomorphism, and go on, a diffeomorphism, okay? As I told you before, the gradients are the guys that we are going to look. It's okay, if you take the deformation zk plus t theta k of x, we are looking for theta with the r jet 0, because we are looking for the sufficiency. We need to have this guy the same r jet than the zeta. So the r jet of theta is 0. If the r jet of theta is 0, this polynomial begins after the weighting with degree bigger than r, okay? We are adding something with degree bigger to do this computation, okay? We calculate the gradient, and we construct the vector field. How many time I have, please? Okay, good, thank you. This is the vector field that I told you. We need to integrate this vector field as many times as we need to compute the CI sufficiency, okay? We are not integrating it, but we need it, we are doing the integration, sorry, to compute the germs, the homeomorphism, the Lipschitz homeomorphism. But here we just need to show that this vector field is Lipschitz then its integration is Lipschitz also, okay? Why I told you, oh, you need to control the gradient, because this eta I here are the vectors that I told you that are perpendicular. When we do the normalization, we are constructing some kind of normalized basis from the gradient of the germ, okay? Considering the projections, these are the guys that we are constructing the vector fields. If you are looking just one page before, zeta plus t theta, okay? N plus 1. If you consider one variable more, the variable t, we have this is eta plus, n plus 1 is nothing more than the last coordinate of the derivatives of the guy. The derivative of f in function of the variable t is theta. Here is the theta I that we did. This case, oh, sorry. Here, we do all the derivatives according to the variables x, and then we take the last derivative in an plus 1, the last coordinate, is the derivative with respect to t, the variable t. So give us the vector field theta I over ne xt squared. This is a modulus, this is a vector, okay? So this is a vector field. We need to control now what kind of vector field is this. This is the main idea. We need to have a filtration of this guy, the filtration according to the set of weights, plus the filtration of this guy must be sometime bigger than the filtration of what is down here to control the integrability of this vector field, okay? And there are some technical lemmas. The first one, I called it the gradient condition. If the gradient of the original f satisfies some inequalities according to the control function, so for that kind of germs, the gradient condition is also satisfied. Very good for us because we must go from here to here. It's quite classical to do this computation. Some remarks, okay? We have the gradient bigger than this condition, so okay, by the statement 2 that our statement 2 is second here. From this statement, we have this inequality. This is very important for us. Moreover, we are looking for a map germ such that the gradients of each one of the coordinate functions are linearly independent because we need a basis from these vector fields. And the class of differentiability is given by f. The gradient has class less L minus 1 as usual. This is another lemma that we can show that this vector field that usually was considered to be a continuous vector field is in fact a Bi-Lipschitz vector field, okay, a Lipschitz vector field, sorry. So if it's Lipschitz, his integration is also Lipschitz. So this is the result that we need. Now we construct the vector field from the original x of xt, subtracting the last coordinate function to get this guy. This is also Lipschitz because of this construction, okay? Then we have the conclusion of the proof, just applying a Picard's theorem of differential equations with initial conditions, okay? If we can apply the Picard theorem to solve this differential equation, we integrate this vector field to get the homeomorphism that we need, okay? This is the construction of zeta equal zeta h plus theta, zeta plus theta h. This is really the condition that we need to get the Bi-Lipschitz sufficiency. Corollary theorem of Favaro-Martins, but in the Bi-Lipschitz point of view. Then we have the theorem for the i-sufficiency, okay? It's the same conditions, but RW are 0W as I defined a little bit before, okay, using the gradient. And this was the example given by Favaro-Martins. It's really homogeneous, so everything works in the same situation. In this is the same jet space that we need, okay? This is the other example that we showed before. The computations of the DIs are done here, but the most important is that we obtain the RW of zeta equal to 5, okay, doing these computations. From this, we obtain this condition, r minus 3 minus 4i bigger or equal than 0. Then we need r bigger or equal than 3 to get this zero sufficiency. Y is like 0 here. And then we can do a deformation of zeta by zeta plus t theta, as I told before. Here is just z plus theta. They are the same realizations of the guy, but the realization in degree 7, okay? This is a monomial that is of class 7, and it is already with weight degree bigger than 7 here, okay? So this guy is C1, in fact, is bigger than 7, yes. It's C1 equivalent to zeta. This here is C1 equivalent to zeta. This was very nice for us to show this kind of equivalence, okay? Here is just the conclusion. There is another example that we did, okay? Doing the same computations here, we compute R0W and RW, and we get 4 plus 4i to take the 1, 2. 1, 2 is the set of weights here, again. Sufficiency, CI sufficiency in CR, okay? And here are the references that we have. Boknaku, Favaro-Martins, as I showed you before, was the main motivation for us to do this paper, together with the reference given by Paunesco here to consider the weighted point of view, okay? And thank you very much for your attention.
Oh, thank you, Marcelo. Oh, any question or comment? For those people that are online.
Sorry?
Those people that are online.
Oh, yes, I forgot.
So let's think this. Come back at
Alô. Nossa, tá bem alto. Posso falar baixinho. Gostoso.
Alô, Sandra? Alô?
Oi.
So can we start again? It is a good pleasure to introduce Professor Miriam from ICMC USP, São Paulo. Thank you very much to visit us here in Vitória. And she is going to talk about stable equilibrium patterns on a ring of identical cells.
Muito obrigada, Valmeci. Thank you for everyone that is here and people that are online. I just want to say a few words. About 5 minutes ago when I got up here, something seemed to get wrong about computer or something, and immediately there were 5 guys around me to help me. So this is what I'm seeing since I arrived here. So obviously I'm very, very happy to be able to come to this event. So I have to thank everyone, Tiago, Leonardo, Leandro, and all the guys that are doing a great job. Thank you very much. Thank you. So this talk is about dynamical networks, which means that we have individual dynamical systems that are coupled in some way and they are interacting. The type of coupling that I will consider is this interaction in a ring, a particular type of coupling then. Here we will see how to use symmetries and algebraic graph theory to investigate, to discover occurrence of critical points and their stability. So this is, I can say that this is in some way related to singularity theory. It's about 7 years when I started to study singularities of vector fields when they are forming a network. So this is something that I'd like to talk today. So here is the summary of what I intend to do. So I'll speak about the Kuramoto model, and I will recognize both the gradient structure of the coupling dynamics and the S1 invariance of the energy function associated with the gradient vector field. Here I'm using this term energy function to push a little bit about the applications that we see in this field. So I'm assuming that the vector field is gradient, and it's the gradient of the function that I'm calling the energy function, right? So about singularities obtained from the list of expected synchronous patterns, and about the achievement of the ground states, namely the critical points of lowest energy, when the number of cells is either even or sufficiently large and odd. So the Kuramoto model, Yoshiki Kuramoto, he's from Kyoto University. He first proposed about 40 years ago what is nowadays the most studied mathematical model to describe and to understand synchronization. There is a huge number of applications what he has proposed in neuroscience, biology, physics, etc. So this picture here, what is showing is a complete graph that is each vertex connected to any other vertices in an identical way. So the connection is represented by the edges of the graph. And the picture here is also illustrating, it's a little bit dark, but you may be able to see that these are the phases. So what we are looking is the position of the oscillator is measured by the angle that it makes with the vertical. So in this picture, we see a kind of what we call total synchrony, because they are all doing the same angle with the vertical. Just as an illustration. So this is an assumption. Oscillators are identical or nearly identical. Individual ones, I mean, okay? We assume all-to-all coupling. The individual dynamics is given by an interaction of a sine-like function depending on the phase difference between each pair of cells. This sum is emphasizing that we have the all-to-all coupling. So this is the dynamics of the individual cell. Okay. Now I brought this slide just to see a little bit of some applications that people are doing in neuroscience, for example. So this picture shows a seizure event related to epilepsy. I brought this because usually we think of synchrony as a good thing. So there are cases where it's not, in an epileptic seizure, for example. So this picture is a comparison between the clinically recorded onset of a generalized seizure event and the output of a modular Kuramoto network down here. Logical model. So in case A above, the epileptic seizure as captured by an electroencephalogram model displays behavior similar to the epileptic seizure. We see the similarity between these two simulations. So in the model, this down here is the paper where I extracted this picture, and the authors assume local networks, not local networks, to be all-to-all coupled. So the local network are these nodes, and they are interacting some way. So each node, so each individual cell, if we compare with the previous slides, the individual dynamics now, depends on the interaction in a node, plus another part depending on its interacting, this is interacting with other nodes, which corresponding to this part here. Okay. So let us move on to the case that I have been studied. So the ring of identical cells. So for each cell I, the graph, we can identify the vector state with its angle. So this is a vector, and it has an angle with the vertical direction. And we measure the dynamics with respect to the variation of theta in time. So because of this, the configuration manifold is the n torus if we have n cells, okay? And as for the Kuramoto model, we assume that the vector field is gradient, and then the admissible function, the total energy, is given by this expression. So each interaction is identical. So this is saying that this is the coupling function depending on the phase differences between neighbor cells. Actually, if we look at this function age, the gradient structure implies that we have this function, which we call a admissible function for this kind of network. And actually, it was a paper with Mike Roberts that we found the general form of any admissible function for graphs. So what about the critical points? In most applications, the critical point, the coupling function is a cosine function. Here we consider slightly more general coupling. So I'm going in the following direction. I want to propose a coupling function which is more general, a little bit more general than a cosine function, which is the one that we see in the Kuramoto model. And then we have to, we impose 4 conditions, which are delta extends to R as an even and one periodic function. Let me just say that 0, 1 is the S1, okay? The circle I am identifying with this closed interval. So delta is 1 periodic. The first derivative, delta prime, vanishes at 0 and 1/2. The second derivative, delta 2 prime, is monotone in the interval, in the open interval. And the second derivative is negative at 0 and positive at 1/2. In other words, the graph is like that. Critical points of this function are points then theta with any entries, such that their derivatives are equal at phase differences of neighbor cells. And the Hessian of this matrix, so the Hessian matrix of this function is directly computed to produce these expressions. And at this point, we see it was the most useful thing in our study, is that we recognize the Hessian as what we call a Laplacian matrix, what we call in graph theory, a Laplacian matrix. So I just bring here a very, very simple example for people that has not seen the matrices associated with graphs very often. So a very simple example, so we can recall it all together here. So we recall that the Laplacian matrix of a graph is the degree matrix minus the adjacency matrix. So D is a diagonal matrix of the degrees of the vertices. A is the adjacency matrix. So for a simple graph like this one, this is the adjacency matrix. So line 1 saying that 1 is interacting with 2 and 4. So 2 and 4 in 1, and 0 and 0 here, and so on. And L in this case is D minus A. This is a regular graph. Every vertex has degree 2. So D is 2 times the identity. Sorry, there is a wrong 2 here. It's 4. 2 times the identity matrix of order 4 minus A. So let me just point out that this matrix is a singular matrix, obviously. So this is the sum of elements in each line is 0, which means that 0 is an eigenvalue, and the eigenvector is all elements, all entries are equal to 1. So if we look at the Hessian matrix of our ring graph, this is not the traditional Laplacian matrix, but it's the weighted Laplacian matrix at any point. And the weight is the ij edge, which is the edge connecting vertex I to j. And this is the weight of every edge. So here I bring the Hessian for n equals 6. So we can see this property that we keep having, which is the sum of each line, the elements of each line equals 0. So in general, without any symmetry constraints, we expect that singularities are Morse. But in this context, we necessarily have a 0 eigenvalue. So proposition for any cell graph G, all critical points of S1 invariant admissible functions on G are degenerate. So no more singularities are to be expected, which is quite what we usually encounter when we have symmetries. It's always something normal to expect more degenerate singularities. So we investigate critical points using symmetries and algebraic graph theory. As I said, this was the main point of my talk, to use these two elements to explore how the critical points appear in the problem, how we find them, and how we find the stability of them. So we have already realized that the coupling function depends on the phase differences. So nothing more natural than introduce the variables that are precisely these differences, okay? Xi is the difference. And then we keep going with this investigation of delta depending on these differences, the xi's. So if we rewrite the formula for the critical point, it's given by this expression here, where the sum of the xi's must be an integer, because when we go around the circle, we should have a multiple of 2 pi. So in coordinates from 0, 1 must be an integer. And I'm calling m the sum of these xi's. So from S1, C1 is the hypothesis that is guaranteeing that this is a one periodic and even. We have the possibility to reduce the domain to 0, 1/2. And m varies from 0 to the number of n, the number of cells over 2. Okay. So we have our function, and we know that the automorphism group of the ring graph is the dihedral group. So H is the Dn invariant and is also S1 invariant because of this structure. So this is Dn cross S1 invariant function for this action of the group on the N torus. So what this is doing, the element of the dihedral group is permuting the indices, and phi, the element in S1, is adding a phase, the same phase phi in each component. So what do? We have to describe the isotropies of this group, and we start to investigate critical points based on these groups, with the idea that we look at these subgroups as their isotropies. So this is the isotropy lattice of this group. There are many cyclic groups here, especially if n depends on the number n. We have another cyclic group here, and this is the trivial group. This tau here this is the permutation that takes 1 to 2, 2 to 3, 3 to 4, etc., and n to 1, and then we close the circle. I'd like to give an example. Do you know what time it is? Que horas são? Hã? Não entendi. Ah, então tem bastante. Tem até 4h20, 4h20, acho. Tá, obrigada. So I'll give some examples, but where are my examples? Yeah, so look, so this is, so when I was saying, we take these isotropies and then we started to compute the critical points for their isotropies. So let's just look in the middle of this table. Sorry. And so for the n, the representative is total synchrony, theta 1, theta 2, all equal to 0. Zn, this is another isotropy, producing this critical point, etc. So it was this knowledge that we used to describe all possible critical point representatives for our problem. Here I'm including the values of the energy function, which is the one that we want to study minimum, and the Laplacian weights. I will be using it in a moment. So let's just look in an example. I'll consider this isotropy, the cyclic group for a ring of 6 cells, the Z6 generated by this permutation, and phi is 1/6, which means that this is the rotation of 2 pi over 6 radians clockwise, and the isotropy subgroup. This is the isotropy group generated by this element. So this is the configuration, the critical configuration with this isotropy. So what's going on here is tau takes theta 1 to theta 6, 6 to 5, so it rotates, it's not rotating, but it's permuting the indices anti-clockwise, simply because, as I defined, the action is a permutation in the indices, but there is a -1. So this is the inverse of tau. So it goes permuting indices clockwise. But what phi does, phi rotates, it adds a phase clockwise. So if we choose phi 1/6, we get to the point again. So suppose that we have this arrow. When you apply this permutation, this phase comes to this one, so we will see this upwards. And then I rotate it of 1/6 and it comes back to this position. In other words, this image is invariant under the action of this cyclic group. Another example, if we replace 1/6 by a half, we should see the phases coming up and down, and this is the angle pi from 1 to 1. That's why I have to pick phi equals to 1/2, rotating of pi radians clockwise. Another example, for two critical configurations with trivial isotropies, so these have no symmetries at all. Coming back to the table, this will produce a critical point as long as the sum of P and Q is n. So these are the two possibilities we have for this case when n equals 6. P and Q can be 3, or one can be 5, and the other one can be 1, meaning that we have 3 phase differences equal to a fixed value, C, so 1, 2, and 3, and here another 3, and the picture on the right, 5 phases, C, 1, 2, 3, 4, 5, and 6, 1 eta. Theorem, so let G be the ring of the n cells with coupling function under the conditions since the beginning, then the stability of these critical points that appear in the previous table is as follows. So I want to, from 1, 2, 3, and 4, describing stability from the isotropies. So starting with this isotropy, the equilibrium is stable. So this is precisely the up and down configuration. For when the sum m is different from 0 and n over 2, in equilibrium of the other type of isotropy is stable if and only if the second derivative at that point is positive. For any odd, a trivial isotropy equilibrium is stable if and only if exactly one pair of neighbors assumes the same state value. Possible trivial isotropy equilibrium associated with two values xi and eta in the open interval 0.5 are stable only if P is n-1 and Q is 1. So this, I'd like just to consider, let's just look at this picture. What we see here is what we call a frustration phenomenon for 5 cells. Let me explain that. So look at the arrows. We see up and down, up and down, up. And if we continue, when n is even, we know that this configuration will produce a stable critical point. But when this is even, it is this result, the number 2 here, 3, is saying that it tends to be up and down, but the number of cells being odd does not permit that. So this is what we call the frustration, because it tends to be up and down, but we necessarily will have this kind of figuration, two neighbors with the same identical phase. This name, frustration phenomenon, we decided to call it because this comes from physics. There are problems in physics called the antiferromagnetism spins, and they check numerically this kind of things happening. So this is what we are checking, that this actually can be a stable configuration. I have an interest to outline the proof of this theorem, because that's where we can see the power of the algebraic graph theory. So for case 1, what we have to do, we have any even, we have disisotropy and want to prove stability. So what we have to do is to compute the Hessian matrix at this point. If we do that, we see that the Hessian is a weighted Laplacian. This is the weight, and this is the traditional Laplace without weights. I was given the example in the beginning. So the n-1 non-zero eigenvalues of L are positive, simply because this is a regular graph. So the Laplacian has this property. And then stability of this point will depend on the sign of this number, which by assumption C4, this is positive. Okay. For case 2 is similar. We all again have a multiple of the Laplacian, but now this is not a hypothesis since the beginning. So if we assume that this number is positive, then we get stability. And then I'd like to have just 2 minutes to discuss about case 4. What is case 4? We are discussing about possible trivial isotropies associated with these two numbers in the open interval of the domain of the coupling function. And this is saying that this is stable if P is n-1 and Q is 1. So if we get a graph with n vertices, we were very pleased actually when we found this result. This is from Bronsky and Deville. It's a paper of 2014. It was very, very helpful to us because so this is saying the following. If you have a graph, let G plus or G minus, so G plus denote the subgroup with subgraph with the same vertex set together with edges of positive weights and G minus for negative weights. So in this case, we would have, there is an edge missing. This is on purpose, but suppose that we have that edge here. And then we have these weights, we have these numbers, and we know that the weights are the second derivatives calculated on C's and these values here. So G plus, I keep the graph G plus by selecting edges with positive weights and G minus for negative weights. Now, we also define three indices, n0, n minus, and n plus, as the numbers of 0, negative, and positive eigenvalues of the weighted Laplacian. And then they give these best estimates for these numbers, the lower and upper bounds for each one. And this is the number of connected components of G plus, and this is the number of connected components of G minus, etc. So what we see is that in order to have stable critical points, necessarily we have to have the number of negative eigenvalues equals 0. So we need to have this number equals 0, which means that the number of this G plus must be connected. Okay, this number must be 1. So G plus is connected. Now, if we look at the hypothesis, this weight is positive and this weight is negative. That's why I bring this picture here, because I'm saying that I need to have G plus connected. And in a ring graph, we can only encounter a connected subgraph if we remove at most one edge, which means that Q must be 1 and P must be n minus 1. And why I'm keeping C, because this is the one that produced the weight positive. Sorry, again, I'm so lost with this pointer. I'm sorry. Okay. Right. And just to finish, this is the proposition that gives the ground states. In other words, the global minimum of the function. And now we have to, so the result is, if n is even, then the ground state of this vector field is given by theta, for which the differences is a constant, is a half. So this, I mean that this is the up-down configuration. When we go around the ring, we will have to have plus and down, these alternating phases. This is the configuration for n even. This is the minimum of the energy function. When n is odd, I think this is a kind of interesting fact, because when n is odd and sufficiently large, so we had to assume that n is sufficiently large. We could not prove this for any number n. We should suppose it's sufficiently large. Then the ground state is given by, it's not constant, so it's not an up and down configuration. But you see what this is, this perturbation is doing. When n is large, this is not up and down configuration, but it looks like an up and down configuration because it's just minus something that's quite small. So the differences are almost up and down configuration. That's why I bring it so it's come to up and down, which is a little bit less than angle pi, and alternates between these two phases. And when it closes, this is not clear in the picture, but I'd like to say that when you close the ring, instead of finding up and down and finish with up, we would finish with down. In other words, when n is odd sufficiently large, this is an almost up and down configuration with frustration. Okay, so I think that's it. I'm getting to the end, and thank you very much for your attention.
Thank you, Miriam. So, any question or comment?
When you look to this structure, it looks like there are several applications for this in chemistry, for instance, or any other kind of situation like cryptography or something like this, because
what
codes? Cryptography,
yes.
Because if you can interfere in the structure, well, with something outside, then you can conserve some information along the singularities. And also, well, there is a myriad of applications, I guess. So do you know some of them or anything related with?
I have never learned anything about cryptography, but it seems to be a very, very interesting idea, because in some way, in this case, I'm just looking at critical points. So steady states related to a dynamics, but we can go further than that. We can analyze the synchrony as a dynamical process. So maybe cryptography must, I don't know. I don't know, but it's
Okay, thank you.
Thank you.
Any other question, please?
Can I just say something?
Sure.
You see that I started with a graph. I fixed the ring configuration of coupling, and we want to analyze the vector field which has a gradient structure. There are other kinds of vector fields associated with a given graph, with a given network, a couple dynamics. So this is something that people are doing since the beginning of this century. But there is a nice question, which is, so instead of having a graph and producing what is the kind of vector field that people call admissible vector fields for this graph, for this dynamics, we can ask the opposite question. So you propose the vector field, you propose the dynamics, and you want to know what kind of connections the individual cells might have in order to produce this vector field, the given vector field as an admissible vector field for a given graph. And I'm just advertising what is an ongoing doctorate program of Tiago, who is here with us, and he proposes the analysis of this question going on the other way. Okay. Thank you.
Any question from the people that are online? Okay, so let's thank the speaker again. So we come back at 16 and 50. Oh, now is the coffee break.
Agora foi.
Estranho. Você já quer falar com todo mundo? Porque daí eu tenho que ligar o microfone do Meet ali.
Eu só tenho que chamar o pessoal lá fora, né?
Ah.
Eles não vieram
Se
ainda.
é pra galera lá de fora?
Vamos lá chamar o pessoal lá, Leandro? 4h50. Dá aquela batidinha de palma lá, chama.
Eu vou falar com a Thaís. Quer falar com a Thaís você?
Não, a Thaís pode meter o português mesmo.
Thaís? Thaís, você tá aí?
Pode ir, já pode ir compartilhando.
Oi.
Oi, sim, tô aqui.
Tudo bem? Daqui a pouco a gente começa, só vamos chamar o pessoal para voltar do coffee break.
Tá bom, obrigada, Carol.
Nada. Você já consegue compartilhar essa tela para a gente organizar aqui?
Consigo sim, só um minutinho. Ah, tá aparecendo aí?
Sim.
Tá sim.
Tá sim. O pessoal está voltando e a gente já começa.
Uhum.
Tu não veio, hein?
Se ela tá vendo.
É contigo mesmo que eu tô falando, Thaís.
O quê?
Era pra estar aqui, Thaís.
Pois é, eu preferia estar aí, com certeza. Tô vendo vocês todos de camiseta, de blusinha, e eu aqui, ó, de roupa de frio, maior frio aqui em São Carlos. Infelizmente, não foi possível.
Consegue?
Thaís, podemos conversar?
Podemos sim, Thiago.
Okay. So we gonna to the last two talks in this afternoon. It's a pleasure to announce our next speaker, Thais Maria Dalbelo from Universidade Federal de São Carlos. She's going to talk about Brasselet numbers and toric varieties. So, Thais.
Thank you, Thiago. Good afternoon and good evening for some of you. First, I would like to say that it is a very pleasure to me to present this talk in this very nice meeting. And I also would like to thank the organizers for the invitation. So I'm going to talk about Brasselet number and toric varieties, which is a joint work with Louise Hartmann. So this presentation is divided in these three topics. First, I'm going to talk about toric variety and some of its properties. After, I'm going to present the definition of Brasselet number and also of the local order obstruction. And lastly, I'm going to present the definition of Newton polygons for functions defined in toric varieties. And I will use these concepts to present formulas to compute the Brasselet number. So let me start with the part of toric variety. So in this presentation, I will denote by M the z-lattice of with rank D, and I will denote by MR this set, which is related to the z-lattice, and we take a finitely generated semigroup S of M such that 0 belongs to S. And we denote by con S the convex rule of S in MR. And in this work, we assume that this con S, is in fact a strongly convex polyhedral cone in MR, such that the dimension of cone S is equal the dimension of the z-lattice M. The group algebra CS is finitely generated over C, and the toric variety that we denote by XS is defined by this way as the spec of this group algebra, where the spec here denotes the ideal of the spec denotes the set of all maximal ideals of this algebra, okay? So let me make an example. So if we consider in Z2 the semigroup S generated by these three vectors, okay? So I draw here this, I did a picture here to represent these three vectors. And these three vectors, they are the generators of the semigroup. However, the semigroup, as you can see, is in the semigroup, there is a lot of points. These are just the generators. So, and we cannot forget that 0 belongs to the semigroup S. So the convex rule of this set in R2 is exactly this set here, which is a cone two-dimensional, a two-dimensional cone, the cone S, okay? And the group algebra CS here is in fact this algebra. Here, the generators of the algebra are related to the generators of the semigroup S. And here, Z1 and Z2 are the variables of I'm sorry, oops, of the ring of Lohan polynomials. So, as we defined before, the toric variety is the spec of this algebra. And it is possible to prove, using, for instance, the Nussstellensatz, that in fact this toric variety is equal to the zero set of the ideal I generated by this binomial. Okay, so in this example, this toric variety is in fact a toric surface with an isolated singularity at the origin. And it is in C3. Okay. The toric varieties, they have a lot of special properties. For instance, giving a toric variety X sigma, it is possible to prove that there exists an action of the algebraic torus into the variety. And also, when we consider the cone S associated to the semigroup S, it is possible to divide this cone into subcones that are very special. And we call these subcones the faces of the cone S. For instance, in the previous example, we use this cone S, and here we have 4 faces. One zero-dimensional face that is the origin. 2 one-dimensional faces that are these 2 rays, and the other face is the whole cone that is a 2-dimensional face. Now, it is possible to prove that there exists a bionivocal relation between the set of the faces of the cone S and the set of the orbits from the torus action. And because of that, we use this notation to represent an orbit of this action. So T delta denote the orbit, which is related with the phase delta, okay? Each of these orbits is isomorphic to an algebraic torus of some dimension R. So we have a decomposition of the toric variety into orbits that are always move. And more than that, this decomposition is in fact a Whitney stratification of the toric variety. Now I'm going to talk about the Euler obstruction and the Brasselet number. The Euler obstruction was defined by Macpherson as one of the main tools of his proof of the line and Grothendieck conjecture. Sometime after, Jean-Paul Brasselet and Maria Schwarz presented an equivalent definition using vector fields. And although it is a very important invariant, the Euler obstruction is not easily computed using its definition. So many authors presented formulas to make the computation easier. For instance, Brasselet, Le, and Sead presented a Lifshitz type formula, a very important formula, in fact, that I present for you here. So they proved that giving X a complex analytic space and V a Whitney stratification of X, then the Euler obstruction of X in a point P is equal to 1 if P belongs to the smooth, to the regular part of X, and on the other hand, if P belongs to the singular set of X, they proved that the Euler obstruction in this point is given by this sum, where L is a generic linear formula, and this term denote denote the Euler obstruction of X in a point of the stratum V alpha. Here, it's very important to say that the Euler obstruction is constant along stratum of a witness stratification. So, because of this, we can use this notation, okay? Now, when we look to this very beautiful formula, there is a natural question that arises, which is, what happens if we change here the linear, the generic linear form for a function that is no longer necessarily a generic linear form? For instance, a function with an isolated singularity at the origin. To answer this question, Brasselet, Massey, Parameswaran, and Sead defined a new invariant that they called the Euler obstruction of a function in X. And the authors, they proved that if f is a holomorphic function with an isolated critical point at the origin, then the Euler obstruction of f in X is given by this formula. And Sead, Tibari, and Verjovsky, they proved this very important result concern about this invariant. They proved that the Euler obstruction of a function is up to sign the number of Morse points in the regular part of the variety, which appears in a stratified Morsification of f. Therefore, the Euler obstruction of f can be considered as a generalization of the Müller number of a function. And now, if we come back to this formula, to this result, we can do another question. In fact, a similar question that was one of the motivations to define this invariant, which is, what happens if we change this function for a function that not necessarily has an isolated critical point at the origin? To answer this question, Dutertre and Grulha defined another invariant that they call the Brasselet number of a function. So, to define this invariant, let us consider V a good stratification of X relative to a function f. Then the Brasselet number of f in X is defined by this sum. And the authors proved that, I'm sorry, now before I need to say here, I will use this notation. For me, X to G denote this intersection, which means the zero set of G in the set X, okay? So if G is a prepolar function with respect to V, which is a good stratification of X, of F, of X related to F, then this difference of Brasselet numbers is up to sign the number of stratified Morse critical points that appears in the top stratum of the stratification V in a Morsification of G. Okay? So now I'm going to talk about Newton polynomials. Consider f a polynomial function defined in a toric variety xs. We use this notation to denote a polynomial function in a toric variety. And in this notation, V denotes an element from the semigroup S. Okay. We define, given a polynomial function on a toric variety, we define the support of F in this way, by this set. So the support of F is an element belongs to this support if its coefficient here in the function is not zero, just that. And using the support of a function, we can define the Newton polygon of a polynomial function. And by definition, the Newton polygon of a polynomial function is the convex hull of this set, where the sum that appears here is the Minkowski sum. Okay. Let me make an example. So let us consider the toric surface from the previous example, and also the semigroup S. Okay, and let us consider this polynomial function defined on this toric surface, which is this polynomial function. So to find the Newton polygon of F, what we need to do is to relate each monomial component of F with elements from the semigroup, right? So, for instance, this monomial term, W2 square, is related, W2 is related with this generator of the semigroup. So, as we have here the square, we need to consider here also a kind of, in fact, is a sum. This generator plus itself. So this monomial term is related with this element of the semigroup, which I draw here. Okay. And also this monomial term, W1, 2, 3. So I'm sorry, 1 is related with this generator. So we need to, this monomial part is related with this element of the semigroup, which I draw here. And we do the same thing for this monomial part, and we get this element of S, which is here. And now what we need to do is for each element in red, we need to consider this. So, for instance, here, when I do the Minkowski sum, what we have is this. It's a kind of translation of the cone S to this point. Here, we need to do the same thing. Also for this point. And finally, we need to consider the convex hull, which is this set. So this set in red is the Newton polygon of this polynomial function in this toric surface, okay? Now I'm going to present some other elements that I will use. So giving delta a face of cone S such that the intersection of delta with the Newton polygon of F is not empty, we will denote by beta e delta the compact faces of this intersection such that this equality is satisfied. Okay, and we will denote by gamma delta E the convex hull of the compact face beta delta E with the origin in L delta, where L delta is the smallest vector space which contains delta.
2 minutes. 2
okay,
minutes.
I'm finishing. And I will denote by this the normalized d-dimensional, delta dimensional volume of this set. Okay. And let us consider f a polynomial function, a non-degenerated polynomial function. Non-degenerated, it means that the function has no critical points in the dense orbit of the torque's action, okay? Here, I will skip from that because I have no time, but I would like just to say that this set, stratification of the zero set of F into the toric variety, which not necessarily is a good stratification related to the function F. However, it's a stratification good enough because we can refine this stratification to find a good stratification associated to it. And with this refinement, we can prove this result here. I don't know if, I think that I don't have time, but for those of you that are interested, I can explain better what is this volume, okay? And I also would like to say that we have a similar result for ICES, and here the volume is much more complicated, but it is still possible. So as I don't have more time, I will skip from that. And here, just to finish, I would like to show the reference that we use in this work. Of course, that we use more, but here is the one that are important to the presentation. And I need to say that this reference from Matsui and Takeuchi is very important in this work. So it is that. Thank you very much, and I'm sorry for the time.
Are there questions, comments for these beautiful results? People online, are there questions? So, well, seems that Edson has a question.
Hi, Thais.
Hi, Edson. How are you?
With that, those formulas, can you get some result about the invariance of the Brasselet number or Euler invariant, Euler obstruction, for example? Like I know that they are C1 invariant. That means they are invariant by C1 diffeomorphism, for example. But I know there is a some people are trying to prove, for example, they are Bi-Lipschitz homeomorph, for example. But in some special cases, can you obtain some positive answer to that?
Yes, thank you, Edson. It is a very interesting question. So at this point, I don't know if we have a positive answer for the Bi-Lipschitz question, but what we have is, for instance, let me come back to the formula that I present here. With I present this one with more details, so I will talk about this one. As I said before, this stratification not necessarily is a good stratification. However, when F has isolated critical point, at the origin, for instance, we can find in the Massey's works that this is in fact a good stratification. This came from the works of Massey. I would like to ask for all of you, sorry, because my English is not good, but and in another work with Hartmann and Nivaldo Grulha and Ellen Santana, for isolated critical set, it works for all varieties, as we can see in Massey's paper. But when we consider toric variety, if f is a non-degenerated function, we prove with Ellen Santana, Nivaldo, and Hartmann that this is a good stratification even when f has a critical set that has dimension 1. So in this case, we can compute this invariant directly using this stratification. And if we consider a family of functions, now answer the question of Edson, if we consider a family of functions that in which the Newton polygon of this family don't change, then what we have is that this invariant also don't change. And for instance, if f has an isolated critical point, this is in fact the Euler obstruction of a function. And if f is a generic linear formula, then this is in fact the Euler obstruction of the toric variety. So in these cases, when we have a family with the property that the Newton polygon don't change, then we have that the constants of these invariants. I don't know if this answers your question, Edson.
Thank you, Thais.
So hello, I
Hello.
also have a question. So it's not really a question. I don't understand enough about. Oh, sorry, your face disappeared. It's it's strange this hybrid way. I'm here in the lecture hall, but you disappear. There you are. So I don't understand enough of Brasselet numbers to really understand everything, but it's just a suggestion. It feels like, so there is a theory that similar to toric varieties describes varieties with smaller dimensional torus acting. So I work on that. And there is a whole industry of people like me, like trying to generalize everything done for toric for this case, which is more general, but similar enough. And it looks like there are Newton polytopes. There are many things that looks like they could generalize smoothly. So it's not really a question. It's maybe there is something to be done there. That's
Okay.
just a question. And if you're free on Wednesday, watch my talk.
Okay, thank you very much.
Further questions? So if there is no question, let's thank the speaker again.
Thank you very much. Thank you very much.
Thank you.
Can I stop share? I think so.
So you may close your screen, please. Yeah, that's nice. So the next speaker shall be Vladimir Barajas Guzmán from Universidad Autónoma de Zacatecas, Mexico. And the title of his talk is a nobile-like theorem for jet schemes of hypersurfaces. The screen is yours, Paul.
Okay, thank you. I share my screen. Okay, can I start?
It's nice.
Yes.
Nice. You can see it perfectly.
Okay. Okay. Well, first, I want to thank the organizing committee for this opportunity. Today, I will to talk about the Nash blow-up and the jet scheme. Okay. I will begin recalling the definition of the Nash and the higher Nash blow-up. Okay. So let X be an irreducible algebraic variety over an algebraically closed field, and I denote by D the dimension of X. Okay. If I take a point in X, I can define this vector space. Okay, is the maximal ideal in P over the maximal ideal in P to n plus 1. Okay, dual. Okay, in the case when n is equal to 1, we can recover the usual definition of the tangent space. Okay. If P is a non-singular point, then the dimension of this vector space is this combinatorial number. Okay? Then this vector space, TP2n X, is an element in the Grassmannian of the rank D. Okay? Now, we consider the morphisms Gn from the X minus the singular points to the Grassmannian, where a regular point P maps to in their vector space. Okay? With these morphemes, we can define the Nash blow-up. Okay? We define Nash n of x has the closure of the graph of Gn in x times the Grassmannian, and denote by Pn the restriction of projection morphemes to x. Okay? Well, the pair Nash 1 of x with P1 is called the Nash blow-up of x, and the pair Nash n of x with Pn is called the higher Nash blow-up of x of order n. Okay? Well, when we talk about of the resolution of the singularities, a natural question is, does something change when we apply the blow-up? Okay? For the Nash blow-up, there is the following result. Okay? The Nobile's theorem. Okay? Over algebraically closed fields with characteristic 0, we have that the Nash blow-up of the variety is an isomorphism if and only if x is not singular. Okay? So for this result, we have two observations. First, this result is only true in characteristic 0. Okay? And the second observation is that this result is only for the Nash blow-up. Okay? But in recent years, many authors are studied different families of varieties and obtained a Nobile's theorem. For example, Daniel Duarte in 2013 studied the normal toric varieties in characteristic 0 for the higher Nash blow-up. Okay, Daniel Duarte in 2014 studied the normal hypersurface in characteristic 0 for the higher Nash blow-up. Okay, Enrique Chavez, Daniel Duarte, and Arturo Giles in 2020 studied the toric curves in characteristic 0 for the higher Nash blow-up. Okay? Daniel Duarte y Luis Núñez Betancourt in 2020 studied the toric normal varieties, F pure varieties, and normal hypersurface, but this word is in positive characteristic and is for the higher Nash blow-up. And in the same year, Daniel Duarte and Luis Núñez Betancourt give a Nobile theorem, okay, in positive characteristic for normal varieties. Okay? Well, following this word, we obtain this result. Okay? Let X be an irreducible singular hypersurface and assume that the jet scheme of X is irreducible and normal. Then the blow-up of the jet scheme at this module is not at isomorphism. Okay? For the rest of the talk, I will define the jet schemes, the module of differentials, who is this ring, and why is the interesting of this module. Okay? So first, I define the module of scalar differentials. Okay? Let A be a K-algebra and denote by I the kernel of the homomorphism product. Okay? the A module omega, I over I squared is called the module of Caylor differentials and is denoted by omega 1. Okay? And the A module omega m, okay, is defined as I over I to m plus 1 and is called the module of Caylor differentials of order n. Okay? Now, I said what it means the blow up of the a module. Okay? Let A be a Noetherian domain and M a finitely generated A module. Suppose that M has a presentation, okay? Then Villamayor, okay, give this theorem, okay? Exists a submatrix L prime of L such that if J be the ideal generated by the maximal Mirnos of L prime, then the blow up of the module M as defined as the blow up of the ideal J. Okay? Now, the follow-up object, first, some examples of the blow-ups of module. If M is the module of Caylor differentials, then the blow-up of omega 1 is the Nash blow-up of spec A. And if M is omega m, then the blow-off of omega m is the higher Nash blow-off of spec A. Okay? Well, now I defined the Hash-Smith algebra. This object let me connect the jet schemes with the algebra commutative algebra, sorry. Okay? So I defined the algebra has the quotient of the polynomial algebra in these symbols, okay, over 8, where the ideal I is generated by these sets, okay? This ring, okay, this algebra is called the Hash-Smith algebra of 8 of order n. Okay, now if we observe this set and if I fix I equal to 1, this is a Leibniz rules. Okay, so the idea of this algebra is a generalization of the usual derivations. Okay, now with this object, I can define the jet schemes. Okay, let X a fin scheme, then the scheme of any jet of X is the spec of the Hash-Smith algebra. Okay, now I fix a notation. I denote by 8n the Hash-Smith algebra of 8 of order n, and by Bn this quotient. Okay? Now, why is interesting this module? Okay? The AL module omega 1 tensor Bn is interesting because these observations. First, Tommaso de Fernex and Roy Docampo prove this formula. Okay? And with this formula implies that the blow-off of this tensor is isomorphic with the blow-up of omega 1 of 8n. But by the Villamayor's theorems, this blow-up is the Nash blow-up of the spec AN. But this is the definition of the jet scheme. So this formula implies that the blow-up of the omega-1 tensor Bn is the Nash blow-up of a jet scheme. And other reason is that the blow-up of this module has a good projectivation properties. So a natural question would be if the AN module omega m tensor Bn, okay, has the same properties. Okay, now this formula is not true for m bigger than 1. Okay, but the question is true that this blow-up is the same that this, I don't know. Okay, but using the Villamayor's theorem, we can study the blow-up of omega m tensor Bn. But it's necessary a presentation of this module. So in the case when A is a finitely generated K-algebra, then the AN module omega m tensor Bn has this presentation. Okay. Well, using this presentation plus the Villamayor's theorems, we can study the blow-up of this module. And with all this, we can obtain the main result. Okay. Now, in this point, I still cannot prove is the blow-up, okay, of this module and the higher Nash blow-up at the jet scheme are isomorphic, but this result is a good indication that they could be. Okay, this is a nobile-like theorem for the blow-up, okay, and relative at this model. Okay, this is all. Thank you.
Are there questions or comments? We have. So let me find the best way to reach it.
The Nobile theorem implies that the Nash blow-up is an algebraic variety. Your result can be implied that the high Nash blow-up is an algebraic variety too?
Okay, sorry, can you repeat me the question, please?
The nobile theorem implies that can be implied that the Nash blow-up is an algebraic variety. So your result can be implied the same to the high Nash blow-up. We can guarantee that the high Nash blow-up is an algebraic variety using your result.
I don't know. Oh, sorry. I don't know. Sorry.
So, can I ask this? Sorry. Hello, everybody. So the Nash blow-up and the higher Nash blow-ups are algebraic varieties by definition. This is not a consequence of Mobile's theorem. This is by definition. So I'm not sure what is the question.
The question is if we can guarantee that the high Nash blow-up is an algebraic variety.
But it is, but by definition, not because of the theorem. It's by definition.
Okay. In the last question, your last result, we can generalize to another singular variety instead the hypersurface?
No, this result we only obtained for the hypersurface. The reason is that this presentation, in the case when A is an hypersurface, this sequence is a Chorus exact sequence. So this implies that this matrix has the maximal rank, and this matrix has an scalonic form. So I use these properties to show this result.
Okay, thank you.
Any other question or comment? People online, are there questions or comments? So it seems that it's okay. Then let's thank the speaker again, please. So we quit here and we resume, we'll come back at 9 a.m. tomorrow, isn't it? So have a nice evening. There are a lot of very well places to enjoy yourselves. So see you tomorrow.
Bye bye. Buena plática.
Bye, Joet.
Já vai desligar.